Yeah, you're right. All right. So now, how do we evaluate this thing? The thing is that we can't really do this integral exactly. So we have to do some sort of approximation scheme. Now the idea is that, if I just say in a simple-minded way, if I were to expand the exponential, say 1 minus beta u, and then plus, beta squared u squared, with summations, of course, L2, blah, blah, blah. This doesn't work. And this doesn't work um, because this potential goes to, it diverges as r goes to 0. So a better approximation, a better expansion is needed. And for that, people have figured out it's easier to use what is called the Meyer f function. All right, can you see my screen?
Yes, sir.
Okay. All right, let me just see if I can bring up my lecture notes on my laptop. All right. So yeah, we are going to use the Myers f function, and the Myers f function is given by e to the power minus beta u of r, and then it's going to be minus 1. And then we can express the partition function as 1 over n factorial lambda 3n, and then integrals over the position coordinates. And then because of exponential, we can write the sums as products, and for each factor we can introduce a Meyer f function. Okay. So this is what we have. So then what we can do is that we can expand we can just basically just expand this product, right? So if we just multiply all these factors, the first term that is we are going to have is just 1. And this is something you'll see quite often in computing partition functions. So the first term is going to be just 1. And then we're going to get all the terms which are linear. So we're going to have I greater than j, f of r, ij. And then we'll have terms which are bilinear. So I greater than j, and then L greater than m, f r I j, f r l m, plus dot dot dot. Is that clear? What we're doing here, we're just multiplying everything here.
Sir, won't we have prefactors in front of f in any case?
No, why?
Um, because we were multiplying like so many 1 plus f, so uh, oh no, I think not.
No, we are not. Yeah, yeah. Well, we are going to just ignore everything above this anyway. So even if there's prefactor, that's not a big deal. Okay. So the first term in this expansion, if you do the integration, is just going to give you a factor of the volume of the gas raised to the power n, right? Because you've got n integrals there. So that's going to be from the first term. So in the second term, that is this term, what we can do is that, we can change our integration. So there will be two factors, right? In the second term, there will be like d cubed, say, r1, d cubed r2, because the second term is over two factors of integral. And then, there's going to be other one. There's of course n factors of integral, Rn, but the f's you're going to have, say, we are looking at the term which is, say, R12. So all the integral from, say, d cubed R3 to d cubed Rn, they're going to be trivial integrals, right? So they're going to give rise to factor of v to the power n minus 2. So these are the two integrals that are potentially non-trivial. But what we can do is that in this integral, we can convert to variables which are the center of mass variable. So R12 is going to be R1 plus R2 by 2, and the relative variable, which we call R12, and that's going to be R1 minus R2. So we can change the integrals. If we change the integral, then the integral over this guy is not going to be, this is going to become a trivial integral. So we'll have another factor of, and you can show that the limits work out, that you get another factor of v. And then what you have is, you have here d cubed r f of r. Okay, so you have only essentially one integral left. So, but the thing is that, there are lots of terms there, because there's also the summation. So so all these terms are going to be identical, and how many terms are there? Well, because there's pairwise, these terms are pairwise, there's going to be, the first guy you can choose in n ways, the second guy you can choose in n minus 1 ways, and and those are interchangeable, so you divide by 2. So this is going to be the number of terms. And when n is large, so n is of the order of 10 to the power 23, we can say this is equal to be half of n squared. N squared is much, much larger than n. Okay, so we can ignore the other term. And therefore, putting this together and then ignoring the higher order terms, and we will see a justification for being able to do that, we are going to have factor of v over n factorial lambda to the power 3n, and then we are going to have 1 plus n squared divided by 2v integral over d cubed r f of r, well, like this, okay? So here we are dividing by v because we are factoring out v to the power n, whereas over here, as you saw here, we had v to the power n minus 2. Okay. Now, up to this term, we can say this is equal to v to the power n n factorial lambda 3n 1 plus n by 2v d cubed r f of r dot 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 to the power n, right? Because if I expand this, I get a factor of n down. Okay, this is a trick that will make our life easier.
So could you re-explain this part?
So up to this term, up to this order of term, these two guys agree, right? Because you have an n here, so if you do an expansion, it's 1 plus, if you do a binomial expansion, right?
Oh, okay.
Yeah. So now this should look familiar. Does this look familiar?
No, sir.
Do you
Like
remember
the
the partition?
refactor would correspond to that of the ideal gas interaction
Exactly.
field.
So this is the partition function of the ideal gas. Okay. So if I cut off my expansion after this term, then I can say the log of our interaction, the partition function of our interacting gas is log of the partition function of the ideal gas plus n times log 1 plus n over 2v times integral d cubed of r f of r. Okay? So now, given the partition function, we can calculate what the free energy is. The free energy of our interacting gas will be the free energy of the ideal gas minus times n log of 1 plus n by 2v integral over d cubed r f of r. Okay? So this is, as you can see, if we assume that n over v is very small and we expand this, this is an expansion in n over v.